Hello teacher, hello students. I am Dr. Tukumma Gitaun and this is chemistry tutorial organized and sponsored by Oromia Education Bureau. And in our previous classes, we have just discussed different topics selected from different schools from Oromia region, which are proposed as difficult topics to teach students. And today, we are also going to discuss about molecular geometry. We will also see the factors affecting ideal bond angles. We will also see what ideal bond angles are. I will tell you this one later. So these are the certain shapes of molecules. So you can see from this one, and we are also going to discuss one by one. So these are the shapes of different molecules having these types. These are lone pairs, okay? But others are bonding pairs of electrons. I will tell you this one later. Okay, so let us start our discussion from base pair theory. All the time, to predict the shapes of molecules, you must use the Lewis structure. That is 2D Lewis structure, and also apply this theory, base pair theory. Base pair is nothing but it is an abbreviation which stands for valency, shell, electron, pair repulsion, and this is a theory, and it is used to study molecular geometry, the shapes of molecules. So there are two different geometries. These are the first one is electron pair arrangement or electronic geometry, and the second one is molecular shape or molecular geometry of the molecules. Therefore, this theory or this model is very helpful to predict the shapes of molecules or to study the molecular geometry of different molecules. That as, for example, lone pairs of electrons on the central atom, or by using bond pairs of electrons. This theory, this model allows us to convert 2D Lewis structure into 3D geometry. So we will also see how to draw the Lewis structure for molecules. If you know how to draw the Lewis structure, and by applying base pair theory, you can easily identify the shapes of molecules or electron pair arrangement of the molecules. Electrons arrange themselves as far apart from each other as possible to minimize repulsions according to base pair theory, or simply electron pairs orient themselves in order to minimize repulsive forces. So all the time think about this repulsion between electrons, because electrons have negative charge and there is repulsion between these electrons. So all the time think about this repulsion to just predict the molecular shapes of different molecules. So there are types of electron pairs. You are familiar about this one. The first one is bonding pairs of electrons. This one form bonds. They may be single bonds, double bonds, or triple bonds. Electrons come together to form bonds, and these are bonding pairs of electrons. The second one is lone pairs. You are familiar about this one, or you can also call them as non-bonding pairs of electrons or unshared pair of electrons. These are simply, they are non-bonding electrons. They do not participate in the bond formation, but bonding pair of electrons participate in bond formation. At the end, you will get single bond or double bond or triple bond. So these are bonds, and these types of electron pairs are known as bonding pairs of electrons, and the second one is lone pairs of electrons. Another one, all the time remember that when we say total electron pairs, this is the sum of bonding pair of electrons and the lone pair of electrons. The sum of these two, bonding pairs of electrons and the lone pairs of electrons, or non-bonding pairs of electrons, or you can also call them as unshared pair of electrons, are simply known as total electron pairs. So because we must use total electron pairs of the molecules to predict their electron pair arrangement, you can also predict the molecular shape of the molecules or the geometry of the molecules by using these pairs of electrons. Okay, so let us come to the molecular geometry. What is molecular geometry? Let us start from the definition of molecular geometry. This is nothing but it is a spatial arrangement of atoms in a molecule. Or you can also just define them as the 3D arrangements of molecules, atoms in space. 3D arrangement. So this is simply the definition of molecular geometry. Molecular geometry can also be named as molecular shape. Remember that lone pairs of electrons repel more strongly than bonding pairs of electrons. Order of repulsion energy. Lone pair repulsion is greater than lone pair bond pair repulsion, and this is also greater than bond pair repulsion. So remember this one to predict the shapes of molecules. Lone pairs reduce the bond angle between atoms. So we will discuss about this one. There are different factors that affect the ideal bond angles. Among them, one is lone pairs. Another, for example, multiple bonds. Also, they have effect on the ideal bond angle. So we will discuss this one. Not only this one. The electronegativity of the central atom. The electronegativity of the terminal atom or pendant atom. The size of the central atom. The size of the pendant atom or substituents can also affect the ideal bond angles. I will tell you this one later. So what is bond angle? Bond angle is nothing but it is the angle formed by two surrounding atoms with the central atom at the vertex. What is ideal bond angle? We can also define ideal bond angles as angles that demonstrate the maximum angle where it would minimize repulsion, thus verifying the Weierstrass theory. So that maximum angle is simply known as ideal bond angle. Okay, another one, electron pair arrangement and the molecular shape. What is molecular shape? I told you about this molecular shape. It is a spatial arrangement of atoms in a molecule, okay, in 3D way, in space. I told you about this one. So the electron pair arrangement is also defined by the sets of electrons, both bonding and non-bonding, or lone pair or unshaped pair of electrons around the central atom. So to predict the electron pair arrangement of the molecules, all the time look at the central atom. What are connected to the central atom? So try to look at these bonding pairs of electrons around the central atom, and also lone pair or non-bonding pair or unshaped pair of electrons. So for example, if you identify them, you can easily predict electron pair arrangement of the molecules. So this is about the electron pair arrangement. Another was the molecular shape. This is defined by the relative position of the atomic nuclei. So to predict the shape of the molecules, all the time look at the atoms. Look at the atoms, terminal atoms as well as the central atom. So by only looking at the atoms, we can easily predict or determine the shapes of the molecules or the geometry of the molecule. Molecular geometry, okay? But in the case of electron pair arrangement, all the time look at the pair of electrons, both bonding pair of electrons as well as lone pair of electrons around the central atom, not on the terminal atom. So all the time look at the lone pair of electrons on the terminal atom, not pendant atoms, or not the terminal atoms, or not the substituents. So all the time electron pair arrangements can be identified or predicted by looking at the pair of electrons, both bonding and the non-bonding pair of electrons. But in the case of molecular shape, all the time look at the atoms, okay, all the atoms, central atom as well as the terminal atoms. This molecular shape affects many of the property of the molecule, like for example molecular polarity, which in turn influence the melting point, boiling points, solubility, and even the reactivity of that molecule. For example, carbon dioxide, its shape is linear, but this one water, this one is V-shape. However, water is polar molecule, but this one is non-polar molecule. So how can we determine the molecular shape of the molecule? First, you must draw the Lewis diagram. This is your first step to predict the shapes of molecules. The second one, tally up electron pairs or count electron pairs, both bonding pairs of electrons as well as lone pair of electrons on central atom. Okay, let me tell you one thing. This Weierstrass model, okay, predicts the shapes of many molecules and polyatomic ions. However, it provides no information about the bond lengths or the presence of multiple bonds. So this is a limitation of base pair theory. All the time, okay, count this double bond and the triple bonds as one area of electron density. So this is your second step to predict the shapes of the molecule. Shape is determined by the number of bonding pairs and the lone pairs. So look at the lone pairs of the electrons around the central atom. Look at the number of bonding pairs around the central atom to predict the shapes of the molecule. So this is also another step that you should think to determine the shapes of molecules. We determine the electron pair geometry only looking at the electrons, both bonding electrons, both bonding pair of electrons, as well as lone pair of electrons. This is for electron pair geometry or electronic geometry. So all the time look at the electrons around the central atom to just determine the electron pair geometry. However, we name the molecular geometry only by the positions of atoms. Look at the positions of atoms to predict the molecular geometry. You are familiar about Lewis electron pair approach. Lewis electron pair approach predicts the number and the type of bonds between atoms in a substance. It also indicates which atoms have lone pair of electrons. However, it gives no information about the actual arrangement of atoms in space. So this is the limitation of Lewis electron pair approach. So all the time remember about this one also. If you know how to draw the Lewis structure, and if you identify the bonding pairs and the lone pairs of electrons around the central atom, you can easily predict the geometry of the molecules or the shape of the molecules, as well as the electron pair geometry for that molecule. Okay, so another point is that usually, I told you about this one, a lone pair, okay, single unpaired electron and any bond, single bond, double bond or triple bond, count each of them as one area of electron density. This is the limitation of base pair model. So if you remember this one, you can easily predict the shapes of molecules. But remember that we ignore lone pairs in the molecular geometry. Only look at the atoms. However, in the case of electronic geometry, look at the electron pairs, both bonding electron pair arrangements as well as lone pairs of electrons. All the atoms that obey the octet rule have tetrahedral electron pair geometry. So totally we have 13 common shapes of molecules. So try to know these 13 common shapes of molecules and also try to identify their bond angles. So I will tell you this one by one, and let us start from the larger molecule, in which its central atom has expanded octets. For example, these molecules are AB6 type. In this AB6 type, we have totally 6 pairs of bonding electrons. AB6, so A is nothing but a central atom. These 6 indicates the presence of 6 terminal atoms, B atoms, okay, number of B atoms. In this case, we have no lone pair of electrons. So, for molecules that have, for example, AB6 type, they can be named as octahedral. Their electronic geometry is octahedral. Their molecular shape is also octahedral. So in this case, we have total pair of electrons. How many total pair of electrons? Totally we have 6 pair of electrons, AB6 type. So totally we have how many bonds? 6 bonds. We have central atom A and one bond with B, this B, another bond with this B, another bond with this third B, with this fourth B, and the fifth B, and the sixth B. So totally we have 6 bonds. Best example is SH6. It has 6 single bonds. It has no lone pair of electrons around the central atom. So this is best example for such type of molecules. It has AB6 type, therefore its electronic geometry is octahedral. Its molecular geometry is also octahedral. The ideal bond angle for such type of molecules is 90 degrees. So try to identify this one. Molecular geometry is also octahedral. It is electronic geometry or electron pair arrangement for such type of molecules is also octahedral. Okay, the second one. From the 13 common shapes, the second one is, for example, from this octahedral AB6 type, if one bond is substituted or replaced by lone pair of electron, it becomes AB5, then E. E is nothing but, it indicates the presence of lone pair around the central atom. AB5E type. Electronic geometry for this molecule is also octahedral. We have how many bonds? 5 bonds. We have how many lone pair of electrons? We have only one lone pair of electron around the central atom. IF5 is best example for such type of molecule. So we can draw the Lewis structure for these type of molecules as this one. So from 6, 1 is lone pair. We have how many bonds? 5 bonds around the central atom. And the molecular geometry for this type of molecule is simply known as a square pyramidal. Square pyramidal is the molecular geometry or the molecular shape of such type of molecules. One best example is IF5. Because we have one lone pair of electron on I central atom for this molecule. However, fluorine, totally we have 5 fluorine atoms in this molecule. Therefore, these fluorine atoms are terminal atoms or substituents. So they are bonded with the central atom iodine with only single bond. And single bond is formed between 2 electrons. Therefore, it is simply known as bonding pair of electron. Therefore, molecular geometry for this molecule or any molecule that has AB5E type is simply known as square pyramidal. IF5 molecule or any molecules that have AB5E type, if you have only one lone pair around the central atom and other 5 of them are bonding pairs, therefore the geometry, molecular geometry or molecular shape for such type of molecules is simply known as square pyramidal. What's the bond angle? It is less than 90 degrees. Why? Because of the presence of this lone pair. I told you that lone pair repulsion is greater than lone pair bond pair repulsion, and that is also greater than bond pair repulsion. Therefore, lone pairs have strong repulsion when compared with bonding pairs. Because of this, the presence of this lone pair, the bond angle is less than 90 degrees. Therefore, lone pairs of electrons affect the ideal bond angles. Okay, the third one. From AB6, if we have 4 bonding pairs, AB4, and we have 2 lone pairs of electrons, AB4E2 type, what is the molecular geometry? Or what is the molecular shape of molecules that have this type, AB4E2 type? Or what is its electronic geometry? What is its electron pair arrangement? So I will tell you about this one. So in this case, totally how many electron pairs? We have totally 6 electron pairs. 4 plus 2. From these 6 electron pairs, 4 of them are bonding pairs. AB4. Okay. These B atoms are bonded with the central atom, and the molecules that have this type, AB4E2 type, okay, they have electronic geometry of octahedral. However, their molecular shape or molecular geometry is square planar. So we can draw the Lewis structure, for example, for these type of molecules as this one. Totally we have 2 lone pairs of electrons. To minimize repulsions, okay, repulsions are minimized by pointing these lone pairs toward opposite sides of this octahedron to just minimize repulsion. We have how many bonding pairs? We have 4 bonding pairs. So to just predict the electronic geometry, connect all the electron pairs, both bonding pairs and the lone pairs of electrons, to just identify the electronic geometry. However, to just predict the molecular geometry or molecular shape for such type of molecules, only look at the atoms. Ignore the lone pairs. So if you connect only the atoms, the shape of this molecule is square planar. It is electronic geometry is octahedral. It looks like this one. So this is the third one. The third common shape of molecules. The ideal bond angle for this type of molecules is also 90 degrees. The fourth one, AB 5 type, okay, AB5 type. In this type of molecules, we have how many bonds? Totally we have 5 bonds, because we have 5 B atoms directly connected to the A atom. That A atom is central atom. Therefore, AB5 type, totally we have 5 bonds. However, we have no lone pair of electrons around the central atom for this type of molecules. Therefore, the electronic geometry for this type of molecules is trigonal bipyramidal. It looks like this one. Draw the Lewis structure for Pi5. This is one best example for a molecule that has trigonal bipyramidal. This is the electronic geometry of this type of molecules, or electron pair arrangement of this type of molecules. Therefore, it looks like this one. All the time, try to look at on 3D way. This molecular shape or molecular geometry is also trigonal bipyramidal, because we have no lone pair of electrons on the central atom. Therefore, the molecular geometry is also trigonal bipyramidal. They have the same shape, okay? Electronic geometry is also trigonal bipyramidal. It is molecular geometry is also trigonal bipyramidal. What is the ideal bond angle for molecules that have AB5 type? It is 120 degree and 90 degree. For example, this one, between these 2 atoms, the bond angle is 120 degree. However, this is axial bond. This also axial bond. This is equatorial bond. This one is also equatorial bond. And this is also equatorial bond. So between the equatorial bonds, the bond angle is 120 degree. And between the axial bond and the equatorial bond, the bond angle becomes 90 degree. Therefore, this is the ideal bond angle for the molecules that have trigonal bipyramidal shape. The ideal bond angle for such type of molecules is equal to 120 degree and 90 degree. All the time, lone pair of electrons are placed on the equatorial position to minimize repulsion. Because, for example, if this bond is replaced by lone pair of electron, the angle between this lone pair of electron and this equatorial bond is 90 degree, only 90 degree. If, for example, this bond is replaced by lone pair of electron, therefore, the distance or the angle between this lone pair of electron and this bond pair is 120 degree. Therefore, they are far apart from each other. So, repulsions can be minimized if lone pair of electrons are placed on the equatorial position, not on axial position. Therefore, always electrons are placed on the equatorial position for molecules that have AB5 types. All the time remember this one. However, in the case of octahedral, it doesn't matter if lone pair of electrons are placed on axial position or on the equatorial position. So this one has no lone pair of electrons on the central atom. On this central atom, this is central atom. However, these are simply known as substituents, or they are terminal atoms. Okay, therefore they are covalently bonded to the central atom. Therefore, we have only bonding pairs around central atom. So molecules that have AB5 types, they are simply known as trigonal bipyramidal. This trigonal bipyramidal it is electronic geometry as well as it is molecular geometry. This Pi5 is one best example for molecules that have AB5 type. So P is central atom, so it is A. Then we have how many iodine atoms? Totally we have 5 iodine atoms. So that means B5. We have no lone pairs of electrons on phosphorus atom, on the central atom. Therefore, it is AB5 type. So, for this molecule, its electronic geometry is trigonal bipyramidal. It is molecular geometry is also trigonal bipyramidal. It is ideal bond angle is 120 degree and 90 degree. If, for example, we have one lone pair of electron around the central atom, if one bond is replaced by lone pair of electron, so what is the electronic geometry for such type of molecule? Electronic geometry cannot change. It is trigonal bipyramidal, because in the case of electronic geometry, all the time look at the bonding pairs as well as the lone pairs of electrons around the central atom. So if you connect both bonding pairs as well as lone pairs, so you will get trigonal bipyramidal shape. So this is the electronic geometry for said type of molecules. It can be drawn as, for example, this one. We have one lone pair of electron that is in equatorial position. I told you about this one. It can never be on the axial position. To minimize repulsion between electrons, this lone pair of electrons can be placed in the equatorial position. SF4, this is one best example for said type of molecules. So the shape, the molecular shape or molecular geometry for this type of molecules is seesaw shape, and its bond angle is less than 120 degrees. Why? Because of the presence of lone pair. Lone pair affects the ideal bond angles of the molecules. I told you about that one. Okay, therefore it is less than 120 degrees and it is also less than 90 degrees. Okay, the sixth one, if for example from trigonal bipyramidal, if you have two lone pairs of electrons and three bonding pairs of electrons, what is this? It is electronic geometry. It is simple. Its electronic geometry is trigonal bipyramidal, because totally 3 plus 2 we have 5 electron pairs. Total electron pairs are 5. From these 5 total electron pairs, 3 of them are bonding pairs and 2 of them are lone pairs of electrons. Therefore, its electronic geometry is trigonal bipyramidal. It is the same. However, its molecular shape changes. Okay, I'll tell you this one. All the time remember this one. Total we have 5 electron pairs, and from these 5 electron pairs, 3 of them are bonding pairs and 2 of them are lone pairs. It is electronic geometry is trigonal bipyramidal. This is the electron pair arrangement of this type of molecules. Trigonal bipyramidal. And one best example is ICl3. Okay, you can easily draw the Lewis structure for this molecule. So iodine, it has how many valence electrons? 7. From 7, it forms bonds with 3 chlorine atoms. And we have left with how many electrons? 4. So totally we have 2 lone pairs of electrons around central atom. What is central atom? Iodine. Why it is central atom? Because of its low electronegativity. Except hydrogen, from all molecules, the atom that has low electronegativity can be considered as central atom. Others are terminal atoms, or you can also call them as pendant atoms or substituents. So this is the Lewis structure for ICl3. I is central atom. A, how many chlorine atoms we have? 3. So B3. How many lone pairs of electrons we have around the central atom? 2 lone pairs of electrons. So E2. AB3, E2 type. So the molecular geometry or molecular shape of this molecule is T shape, and its bond angle is less than 90 degrees. It looks like this one. We have 2 lone pairs of electrons around the central atom. So repulsion between these 2 lone pairs is greater when compared with other bonding pairs. So it decreases the ideal bond angle, and it looks like this one. The molecular shape is T shape, but electronic geometry is trigonal bipyramidal, because we have totally 5 electron pairs around the central atom. So to just identify the electronic geometry, look at the electron pairs around the central atom. So at the end, you can easily predict the electronic geometry for that molecule. In the case of molecular geometry, or in the case of molecular shape, look at the atoms, ignore the lone pairs. So the molecular geometry for this type of molecules is T shape. Its bond angle is less than 90 degrees. The 7th one, okay, if we have 3 lone pairs of electrons around the central atom and 2 bonding pairs of electrons, its electronic geometry is the same, trigonal bipyramidal, because totally we have how many pairs of electrons? 5. 2 plus 3, okay, 2 plus 3 equal to 5. This is total electron pairs. From these total electron pairs, 2 of them are bonding pairs and 3 of them are lone pairs of electrons. So we have 3 lone pairs of electrons around the central atom, and only we have 2 bonding pairs. So what is it? Is electronic geometry? It is simple. Electronic geometry is the same, trigonal bipyramidal, because of the presence of these 5 electron pairs around the central atom. So to predict the electronic geometry, look at the total electron pairs. I already told you about that one. However, it is molecular geometry is different. Iodine is one best example of a molecule that has Ab2E3 type. Okay, so it is molecular geometry is linear. The bond angle for this type of molecule that has linear shape, is equal to 180 degree. So try to draw the Lewis structure for I3 minus iodine. So you can easily draw, for example, I. Okay, it is directly bonded with another iodine atom and another iodine atom also. This is central atom. These are terminal atoms. So we have how many lone pairs of electrons? 3 lone pairs of electrons. So this is for iodine. And this is, for example, this is central atom A. These are terminal atoms. How many atoms we have? 2, Ab2. How many lone pairs of electrons we have around central atom? 3. So Ab2E3 type. Ab2E3 type. Therefore, it is electronic geometry is trigonal bipyramidal, and it is molecular geometry is linear. It is bond angle is 180 degree. The A1 is Ab4 type of molecule. So in this case, totally we have 4 electron pairs around the central atom. We have 4 bonding pairs, and we have no lone pair of electrons around the central atom. So molecules that have Ab4 types, their electronic geometry is tetrahedral. The best example is CH4. This is methane or CCl4. These type of molecules, they have Ab4 type, and their electronic geometry is tetrahedral. And their shape is also tetrahedral, because we have no lone pairs of electrons around the central atom. So it looks like this one. So this is the shape, okay? The shape of say type of molecules. The molecules that have Ab4 types, their electronic geometry is tetrahedral. Molecular shape is also tetrahedral. Why? Because we have no lone pairs of electrons around the central atom. What is their ideal bond angle? Their ideal bond angle is 109.5. 109.5 degree is the ideal bond angle for say type of molecules. So this is the A's common shape of molecules. This is the Lewis structure for this molecule. Carbon is central atom, A, okay? And hydrogen atoms are terminal atoms, B. How many hydrogen atoms we have? 4. So Ab4. We have no lone pair of electrons. Therefore, the electronic geometry for this molecule is tetrahedral. The molecular geometry is also tetrahedral, and it is ideal bond angle is 109.5. The ninth one, from tetrahedral arrangement, if one bond is replaced by 1 lone pair of electron, what is the electronic geometry for this type of molecules? What is the molecular geometry? So I'm going to tell you about this. It is electronic geometry is tetrahedral, the same. Why? Because in the case of electronic geometry, I told you many times that only look at the total electron pairs around the central atom, both bonding pairs and the lone pairs of electrons. But in the case of molecular geometry, look at the atoms, ignore the lone pairs, and connect all the atoms. Then try to look at the shape, and you can easily identify the shape of that molecules. So in this case, the total number of bonds are 3, B3, okay? These 3 indicate the total number of the terminal atoms surrounding the central atom. What is central atom? A is central atom. E is nothing but lone pair of electron. How many lone pair of electrons we have? Only 1 lone pair of electrons. So totally we have 4 electron pairs. Therefore, any molecules that have AB3E types, their electronic geometry is tetrahedral. Trigonal pyramidal is the molecular geometry for molecules that have AB3 E-type, okay? From the 4 bonds, 1 is replaced by lone pair of electron. So we have only 1 lone pair of electron. And we have totally 3 bonding pairs of electrons around the central atom. This is central atom. These are terminal atoms or surrounding atoms or substituents. So electronic geometry is tetrahedral. Trigonal pyramidal is the molecular geometry or the molecular shape for say type of molecules. The bond angle deviates from the ideal bond angle. It is less than 109.5 degree. NCl3 is one best example. The valence electron for nitrogen is 5. Therefore, the Lewis structure for this molecule can be drawn as we have 1 lone pair of electron on nitrogen atom, on the central atom, and there is bond between nitrogen and the chlorine atoms. Totally we have 3 chlorine atoms. So we have 3 bonding pairs. One is also with this chlorine, another with the third chlorine. So this is the Lewis structure for NCl3. And from this one, N is central atom, A. We have totally 3 chlorine atoms. So B3. And we have only 1 lone pair of electron. This is lone pair. That is E. AB3 E-type. So the shape of this molecule is trigonal pyramidal. This is a molecular shape or molecular geometry. It is electronic geometry is tetrahedral because look at the electron pairs to predict the electronic geometry for say type of molecules. So this is the 9th common shape of the molecules. Okay, the 10th one. If for example, one bond is replaced by lone pair of electron, AB2 E2 type. Okay, for AB2 E2 type, totally we have 4 electron pairs. 2 plus 2 is 4. And from these 4 total electron pairs, 2 of them are bonding pairs. And 2 of them are lone pairs of electrons around the central atom. So 2 plus 2 is 4. In the case of electronic geometry, I told you that look at the electron pairs, both bonding and the lone pairs of electrons. So the electronic geometry is the same, tetrahedral, because totally we have 4 electron pairs around the central atom. However, bent shape is a molecular shape for say type of molecules. Bent or V shape or angular shape. What is the bond angle? The bond angle is less than the ideal bond angle. The ideal bond angle for say type of molecules is 109.5 degree. So the angle, the bond angle for this type of molecules is less than 109.5 degree. One best example is water molecule, H2O. Can you draw the Lewis structure for this molecule? We have 2 lone pairs of electrons on oxygen atom, because oxygen is central atom in this shape, in this molecule. And we have how many terminal atoms? 2. What are these 2 atoms? Hydrogen atoms. So this is the Lewis structure for water molecule. And we have oxygen as central atom, so that is A, and we have 2 terminal atoms. These are hydrogen atoms. That is B2, and we have 2 lone pairs of electrons, E2. So this is AB2 E2 type. Molecules that have AB2 E2 type, it is electronic geometry is tetrahedral, but it is molecular geometry is bent shape, V shape. It looks like this one, okay? V shape is molecular shape for say type of molecules. Bond angle is less than 109.5 degree because of the presence of these 2 lone pairs of electrons. Because repulsion is greater between these 2 lone pairs of electrons. Okay, the 11th common shape of molecules is molecules that have AB3 type. In this AB3 type, we have 3 bonding pairs, but we have no lone pairs of electrons on the central atom. Therefore, the electronic geometry for said type of molecules that have AB3 types, is trigonal planar. It looks like this one, planar arrangement. What type of planar? trigonal planar. This is the electronic geometry for the molecules that have AB3 types. Their molecular geometry is also trigonal planar. The ideal bond angle of the molecules that have AB3 type, this type is 120 degree. This is the ideal bond angle. Okay. What is the electronic geometry? Trigonal planar. Remember this one. What is the molecular geometry? Trigonal planar. Why? Because we have no lone pairs of electrons on the central atom. If there is lone pair of electron, the molecular geometry is different from the electronic geometry. BF3 is one best example. You know that boron has 3 valence electrons. So electrons are shared with fluorine atom. Totally we have 3 fluorine atoms, bonding pairs around central atom. Therefore, the angle is 120 degree. This angle is also 120 degree. This angle is also 120 degree. B central atom. A, okay. How many fluorine atoms we have? 3 fluorine atoms. So B3, we have no lone pair of electrons. Therefore, BF3 is a molecule with AB3 type. Therefore, its electronic geometry is trigonal planar. It is molecular geometry or molecular shape is also trigonal planar because we have no lone pairs of electrons around the central atom. If one bond is replaced by lone pair of electron, what is the molecular geometry for said type of molecules? This is the 12th common shape of molecules. Okay, let me show you that one. Okay, so AB2E type. From AB3 type, if one bond is replaced by lone pair of electron, so it becomes AB2E type. So from this one, totally we have 3 pair of electrons. From these 3 pair of electrons, 2 plus 1, 3, 2 of them are bonding pairs, and 1 is lone pair of electrons around the central atom. Therefore, its electronic geometry is the same, trigonal planar. Because in this case, all the time look at the total electron pairs around the central atom. So the total electron pairs are 3 total electron pairs are there around the central atom. Therefore, its electronic geometry is trigonal planar. What is the shape? What is the molecular shape? What is the molecular geometry for said type of molecules? We have 1 lone pair of electron around the central atom and the 2 bonding pairs, and their molecular geometry is bent shape or V shape. What is the bond angle for said type of molecules? Less than 120 degree. Why? Because of the presence of lone pair. It decreases the bond angle from 120 degree. So less than 120 degree is the bond angle for said type of molecules. So one best example is sulfur dioxide. You can easily draw the Lewis structure for sulfur dioxide. S, okay. Here double bond with oxygen, and we have left with only 1 lone pair of electrons around the central atom. Only look at central atom. Lone pairs around central atom. So this is a Lewis structure for sulfur dioxide. S is central atom. A. How many oxygen atoms we have? 2. So B2. Okay. How many lone pairs of electrons we have around central atom? Only 1 on the central atom. So AB2E type. And the molecules that have AB2E types, their electronic geometry is trigonal planar, but their molecular geometry or their molecular shape is bent shape or V shape or angular shape, and their bond angle is less than 120 degree. This is the 12th most common shape of the molecules. For all molecules that have AB2E type, their electronic geometry or their electron pair arrangement is trigonal planar, but their molecular geometry or molecular shape is bent shape or V shape or angular shape, and their bond angle is less than 120 degree. The last one, or the 13th common shape of molecules, is molecules that have AB2 type. In this case, totally we have 2 bonding pairs, but we have no lone pairs around the central atom. So all molecules that have AB2 types, their electronic geometry is linear. Their molecular geometry is also the same, linear. Why? Because we have no lone pairs of electrons around the central atom. On A, okay? Carbon dioxide is one best example for molecules that have AB2 type. So the electronic geometry is linear, its molecular shape is also linear. Molecular shape, okay, it looks like this one. What is ideal bond angle for such type of molecules? 180 degree. Can you draw the Lewis structure for carbon dioxide? Okay, we have double bonds between carbon and oxygen atoms. So this is the Lewis structure for carbon dioxide. Carbon is central atom. Oxygen atoms are surrounding atoms, terminal atoms. So this is A, B2 type. Carbon is A, oxygen atoms are B. So AB2 type. It is electronic geometry is linear. The molecular geometry or molecular shape is also linear. The same geometry. Because we have no lone pairs of electrons around the central atom. And the ideal bond angle is 180 degree. How can we write Lewis structure? I want to tell you some important main pointers in drawing the Lewis structures of the molecules. There are steps, okay, to write the Lewis structures of any molecules. The first one is tally up or count the number of valence electrons. For neutral molecule, this is equal to the number of valence electrons of the constituent atoms. Let us see example, okay. This is methyl nitrite. In this molecule, each hydrogen contributes 1 valence electron. Why? Because the valence electron for hydrogen atom is 1. And we have only 1 carbon atom. And this carbon contributes 4 valence electron. And we have only 1 nitrogen atom in this molecule. And the valence electron for nitrogen atom is 5. So it contributes 5 valence electron. And totally we have 2 oxygen atoms. And the valence electron for 1 oxygen atom is 6. So add them together. Totally we have 24. This is the total valence electrons for the molecule. So this is your first step to write Lewis structures for the molecules. The second one, connect the atoms by covalent bond represented by a dash. Okay, so connect all atoms with single bonds. This is your second step to write the Lewis structure for the molecule. For the same example, okay, the partial structure is this one. Connect all the atoms with single bonds. All the atoms are connected with single bonds. So this is your second step to write the Lewis structure for the molecules. Third step, subtract the number of electrons in bonds from the total number of valence electrons of the molecule. What is the total number of valence electrons for the same molecule? For methyl nitrite, 24 electrons. And how many bonds we have? 1, 2, 3, 4, 5, 6. And 6 bonds are formed from 12 electrons. Because one bond is formed by sharing of 2 electrons. So 24 minus 12, we have left with 12 more electrons. Fourth step is add electrons in pairs so that as many atoms as possible have 8 electrons. So start with most electronegative atom. Okay, from oxygen and nitrogen, which one has high electronegativity value? It is obvious. Oxygen has high electronegativity value when compared with that of nitrogen. What is electronegativity value for oxygen? It is 3.5. What is electronegativity for nitrogen atom? It is equal to 3. So 3.5 is greater than 3. So all the time start from the most electronegative atom. Now we have 2 lone pairs of electrons on this oxygen atom. And it fulfills octet rule. Totally we have 8 electrons around oxygen atom. This oxygen also. How many lone pairs of electrons? 3. We have 1 bonding electrons. So totally we have 8 electrons around this oxygen atom. But look at nitrogen atom. We have how many lone pairs of electrons? 1. And we have 2 bonding pairs. Totally we have 6 electrons. this one does not fulfill octet rule. So use the fifth step. What is fifth step? Try multiple bonds, okay, using the lone pairs on the adjacent atoms. Nitrogen has only 6 electrons, so to fulfill the octet rule, multiple bonds must be used, either double bond or triple bond. So if an atom lacks an octet, use electron pairs on an adjacent atom to form double or triple bond. Examples, there are 2 ways this can be done. One is double bond is formed between nitrogen atom and this oxygen atom. The second one, another way, okay, is double bond is formed between this nitrogen and the oxygen atom. So we have 2 ways for this molecule, methyl nitride, okay. So which one is the most stable in structure? How can we identify whether this one is stable or this one is stable? So use the 6th step. 6th step is calculating formal charge. Formal charge is nothing but it is hypothetical charge the atom has in the molecule or ion. It works for ion. It also works for molecules. So this hypothetical charge of an atom is simply known as formal charge. So calculate formal charge. How can we calculate? Formal charge of an atom can be calculated by using this formula. It is equal to number of valence electron for neutral atom minus number of unshared electrons plus half of number of shared valence electron. So by using this formula, you can easily calculate the formal charge for all atoms in the molecule. Because an atom is assigned, all of it is unshared valence electrons and half of it is shared valence electron. And the formal charges must sum up to the actual charge on the species, 0 for molecule and ionic charge for polyatomic ions. And also there are general pointers that govern the most reasonable least structure based on formal charges. Smaller formal charges are preferable to larger one. And the second one, like charges on adjacent atoms are not desirable. For example, XY, if you have negative charge on X and also negative charge on Y, so these like charges on adjacent atoms are not desirable. So remember this one also. So this is also main point. The third one, a more negative formal charge should reside on more electronegative atom. So which one is more stable, least structure for the molecule? Methyl nitride. So let us calculate. Calculate the formal charge for each atom. Okay, let me tell you only for one atom. For this oxygen atom, let us calculate the formal charge for oxygen atom. What is the valence electron for oxygen? It is equal to 6 minus what is the number of unshared electrons? Number of unshared electrons, 1, 2, 3, 4. We have 4 unshared electrons on oxygen atom. Plus half of what is the number of shared valence electron? 1, 2, 3, 4. Because we have 2 bonds and one bond is formed from 2 electrons. 2 times 2 equal to 4. 4. Therefore 4 divided by 2, it is equal to 2. Plus 4 minus 6. So 6 minus 4 plus 2, 6. This is equal to 0. The formal charge for this nitrogen atom is also equal to 0. The formal charge for this oxygen atom is also equal to 0. Because of this one, by comparing the formal charges of the atoms, this is the most stable least structure for this methyl nitride. For methyl nitride, because none of the atoms possess a formal charge. Because of this reason, this structure is the most stable least structure for methyl nitride. So you can easily just select the stable least structure for the molecules by calculating the formal charges. Okay, so this is the summary of the general patterns to predict the shapes of molecules. I already told you about this one. So molecules that have AB6 type, AB5E type, AB4E2 type, the total number of electrons for all of them is equal to 6. 6 0, 5 1, 4 2, add them together. So the molecular geometry for such type of molecules is octahedral, and these are examples for such type of molecules. If you have one lone pair of electron, that is square pyramidal. Two lone pairs of electron, square planar. But four of them are bonding pairs. So these are examples. These are examples for molecules that have square pyramidal shape. And the bond angle, ideal bond angle is 90 degree. And central atom has sp3d2 hybridization. This is a hybridization for the central atom. Okay, let me show you this one. B. So totally we have how many B atoms? 6. S orbital has only one orbital. So give this one S. P orbital has 3 orbitals. So go to up to 3. P. And the D orbital has 5 orbitals. But we have left with only 2 bonds. So give D. Okay. So S. How many P orbitals? P3. And totally we have 2 D orbitals. sp3d2 is the hybridization for the central atoms for all of them. If you have lone pair, so give one orbital for that lone pair. For all of them, the hybridization for the central atom is sp3d2 hybridization. 5 total pair of electrons, 5 trigonal bipyramidal. So this is electron pair arrangement, electronic geometry, molecular geometry. If there is no lone pair, trigonal bipyramidal. If you have one lone pair of electron, seesaw, these are examples. If you have 2 lone pairs of electrons, but 3 of them are bonding pairs, that is T-shape. These are examples. For example, this type of molecule, 3 lone pairs, 2 bonding pairs, linear, these are examples. And the hybridization for the central atoms, for all of them, is sp3d hybridization. And the bond angle is 90 degree and the 120 degree. So these are the ideal bond angles. For tetrahedral, AB4, AB3, if one bond is replaced by lone pair, and if 2 of the bonds are replaced by lone pair of electrons, their electronic geometry the same, that is tetrahedral. But the shape of this one, molecular geometry or molecular shape is tetrahedral. For this one, trigonal pyramidal, and for this one, V shape, bent shape, angular. These are examples. For AB3 type, trigonal planar, okay, molecular geometry and electronic geometry are the same for say type of molecules. If you have no lone pair of electrons around the central atom, if one bond is replaced by lone pair of electron, V shape or bent or angular, these are examples. AB2 type, linear, these are examples. So hybridization for this one, sp3 for the central atom. For the central atom, for molecules that have this type, okay, sp2. For this type, linear arrangement, sp hybridization. So these are summary of the molecular shapes or molecular geometry of the molecules. This is also summary of bonding arrangement. Totally we have 5, okay, such type of arrangements. Arrangements in which if there is no lone pair of electrons on the central atom, or molecules in which the central atom has no lone pair, AB2, AB3, AB4, AB5, AB6. The shapes looks like this one. This is octahedral. This is trigonal bipyramidal, tetrahedral, trigonal planar, and this one is linear. B is central atom. This is best example. This also example for AB3 type, example for AB4 type, example for AB5 type, and example for AB6 type. So these are molecules in which the central atom has no lone pair. Okay, so it is time to practice. Look at this example. This is selenium oxide. Okay, so this is the leaf structure, SeOOO. We have no lone pair of electrons around the central atom on Se. So what is the electronic geometry for this molecule? The electronic geometry is trigonal planar. Why? Because it is an AB3 type. It looks like this one. We have no lone pair of electron. So electronic geometry is trigonal planar. It is molecular geometry is also the same, because we have no lone pair of electrons around the central atom. So it is also trigonal planar. It is bond angle is 120 degree. Already we have discussed about this one. Okay, for the second one, ASH3, arsine or arsenic hydride or arsenic trihydride. So this is the name of this molecule.
So this is the leaf structure for the molecule. Try to draw by yourself, okay? So this is the leaf structure. This one is A, central atom. And we have 3 terminal atoms, hydrogen atoms. So B, 3. And we have 1 lone pair of electron, E. What is the electronic geometry? The total pair of electrons are 4. So its electronic geometry is tetrahedral because of the presence of 1 lone pair on the central atom and the 3 bonding pairs around the central atom. The molecular geometry or molecular shape is trigonal pyramidal, but its electronic geometry is tetrahedral shape. Shapes of larger molecules. Shapes of larger molecules with more than 1 central atom are different in different parts of the molecule. For example, look at this molecule, CH3COH. This is acetic acid or ethanoic acid, but this is ethanol or ethyl alcohol. Each of them have 3 central atoms, while in C2H4, this is ethene or ethylene, we have 2 central atoms in this molecule. So we assign the geometry about each central atom separately. For example, in this case, it is an AB4 type. We have no lone pair of electrons on the carbon atom. So this is tetrahedral. On this carbon, 2 oxygen double bond, and it also bonds with this carbon. It also bonds with oxygen atom. So it is an AB3 type. We have no lone pair of electron because carbon obeys octet rule. The shape of this molecule at this central atom is trigonal planar. It is an AB3 type. We have no lone pair of electron. But on oxygen atom, we have 2 lone pairs of electron. Therefore, its electronic geometry is tetrahedral, but its molecular geometry is V-shape because of the presence of 2 lone pairs of electrons. For ethanol, at this carbon, its shape is tetrahedral. It is an AB4 type. At this carbon also it is tetrahedral because it is an AB4 type. But at oxygen as a central atom, the shape of this molecule is V-shape. Its electronic geometry is tetrahedral. Try to identify this one. For ethylene, the shape of this molecule at this carbon is trigonal planar. Its electronic geometry is also trigonal planar. Its molecular geometry is also trigonal planar. At this carbon center is also trigonal planar. So we assign the geometry about each central atom separately for larger molecules. Okay, another factors affecting ideal bond angle, effect of multiple bonds, effect of lone pairs, electronegativity of central atom, electronegativity of terminal atom, the size of the central atom, size of terminal atom. All these are factors that affect the ideal bond angle. When multiple bonds, lone pairs, or different surrounding atoms are present, the bond angles deviate from the ideal bond angles. Ideal bond angles is nothing but it is the maximum angle. Already I told you about this one. So if there is lone pair of electrons along the central atom, if there is double bond, the bond angles deviate from the ideal bond angles. Electrons in multiple bonds repel more than the electrons in single bond. Let us see one example, phosgene or carbon dichloride. So this is a structure, okay, for phosgene. So we have carbon to oxygen double bond. This bond angle is 124.3 and this bond angle is 111.4 degree and this bond angle is also 124.3. Therefore, because of the presence of double bond, this double bond affects the ideal bond angle. So this is one factor. Okay, another factor is the presence of lone pairs. If lone pairs around the central atom increases, the bond angle decreases. We have no lone pair of electron on this carbon atom, but we have only 1 lone pair of electron on nitrogen atom, this central atom. And we have 2 lone pairs of electrons on oxygen atom. Oxygen is central atom in this molecule. So lone pair increases, but the bond angle decreases from 109.5 degree to 104.5 degree. Therefore, all the time, remember that the bond angle decreases as the number of lone pairs increase. So try to remember this one also. So this is the second factor. The state of hybridization of the central atom, electronegativity and the size of the atoms involved are also common factors to take into consideration. So these all are also factors that affect the ideal bond angle. Okay, let us see the state of hybridization. As S character increases, or as the percentage of S increases, the bond angle increases. So they are directly proportional. So try to remember this one. Look at this example. For example, for molecules that have an sp3 hybridized central atom, its bond angle is 109.5 degree. sp2 hybridized 120 degree. sp hybridized 180 degree. Its bond angle is 180 degree. Linear shape. Here, the bond angle is 120 degree. This is trigonal planar shape. And this one is tetrahedral shape at each carbon atom. Therefore, this bond angle is 109.5 degree. So the bond angle increases as S character increases, or percentage of S increases. Percentage of S for this sp hybridized atom is 50%. Why? Because we have one S and one P orbital. So 1 divided by 2 times 100. 100 divided by 2 is 50%. But in this case, 1 divided by 3 times 100. 100 divided by 3 is 33.3. In this case, 1 divided by 4 times 100, that is 25. 25, 33.3, and this one is 50. S character increases. Bond angle also increases. They are directly proportional. So state of hybridization of the central atom also affects the ideal bond angle. Another one, electronegativity and the size of the central atom. More electronegative the central atom is, more will be the bond angle. If the electronegativity of the central atom increases, the bond angle also increases. Why? Because electrons repel each other around the central atom. So electronegativity is also directly proportional to the bond angle. As the size of the central atom increases, the bond angle decreases. They are inversely proportional. If the size of the central atom increases, the bond angle decreases because of steric hindrance. Okay, you are familiar about steric hindrance. Okay, let me show you one example. As the central atom increases in size, the bond length also increases, and the pendant atoms are farther from each other in space. This one reduce the bond angles. So these are best example. All of them have trigonal pyramidal shape. The electronegativity of nitrogen is greater than that of phosphorus, and the electronegativity of phosphorus is greater than As, arsenic, and the electronegativity of As is greater than Bi. As electronegativity increases from this one to this one, the bond angle also increases. The bond angle for this one is 106.6, almost 107, and it decreases. Why? Because electronegativity decreases. They are directly proportional. But when we see the size of the central atom, Br has larger size when compared with As. As has larger size when compared with P, and it has larger size when compared with that of nitrogen. So this one has larger size but smaller bond angle. This one has smaller size but larger bond angle. Therefore, the size decreases but the bond angle increases from BiH3 to NH3. All of them have trigonal pyramidal. I already told you about this one. Another one is electronegativity in the size of the pendant atom or pendant group or terminal atom. More electronegative substituent decreases the electron density on the central atom, thus decreasing the bond angle. So they are inversely proportional. As the electronegativity of the substituent increases, the bond angle decreases. This is one best example. Look at the electronegativity of pendant atoms: fluorine, chlorine, bromine, iodine. However, the central atoms are constant. Only we have oxygen atoms in all of these molecules. Therefore, electronegativity decreases from iodine to fluorine. Fluorine is the most electronegative atom when compared with other atoms in all of these molecules. Therefore, as electronegativity of the pendant atoms increases, the bond angle decreases. This molecule has smaller bond angle, 103 degree, and this molecule 110 degree. Why? Because of the electronegativity of the pendant atom or the surrounding atom. Look at this example, and you can also compare the electronegativity of pendant atoms with the bond angles for each of the molecules based on the electronegativity of these atoms. Okay, as the size of the pendant atoms increases, the bond angle increases. This is because of steric hindrance. For example, look at this molecule, water, F2O, chlorine. This one has high bond angle when compared with other. Okay, because the size of pendant atoms, if it is increases, the bond angle also increases. In this case, they are directly proportional. As the size of the pendant atoms increases, the bond angle also increases. The size of chlorine is greater than that of fluorine. Therefore, the bond angle for this molecule, that has chlorine, but the same central atom with this molecule has larger bond angle when compared with F2O. And also compared with H2O. H2O has smaller size. Therefore, the bond angle for water molecule is only 104.5. The bond angle increases because the size of the pendant atoms also increases from hydrogen to chlorine. So we can also compare the size of the pendant atoms with the bond angles of the molecules. So this is also another factor that affects the ideal bond angles of the molecule. Already I told you that it is because of sterics. So molecules with trigonal pyramidal shape are also shown below. They are arranged according to increasing size and decreasing electronegativity of the central atom and pendant atoms. So look at these molecules. Electronegativity decreases down the group. The bond angle also decreases. They are directly proportional. So the electronegativity of central atom as well as the pendant atoms and the size of the central atom as well as the pendant atoms affect the bond angles, as you can see from all these molecules. So this is all about molecular geometry and the factors that affect the molecular geometry. So let us practice, okay, by answering these questions. Okay, question number 1 says, which species has the largest XAX bond angle, where A is the central atom? BF3, AB3 type. We have no lone pairs of electrons. So the bond angle is 120 degree. But this is tetrahedral. We have no lone pairs of electron. It is bond angle is 109.5 degree. This also tetrahedral. But this is V shape. V shape, okay? The bond angle is almost 104.5 degree. This is tetrahedral, 109.5 degree. Therefore, this one has larger bond angle when compared with other molecules. So, A is the correct answer for this question. A neutral molecule having the general formula AB3 has 2 unshared pair of electrons on A. We have AB, AB3 type. How many bonds we have? Totally we have 3 bonding pairs. Okay? And it has also 2 unshared pair of electrons. We have 2 lone pair of electrons. This is given. So the question is that what is the hybridization of A? If this is S, P, P, P up to 3, because P has 3 orbitals and we have left with only 1 bond and give that one D. So we have sp3d. This is the hybridization of the central atom, sp3d. C is the correct answer for this question. Okay, question number 3. It says, what is the electron set and the molecular geometry of IF4 plus polyatomic ion? We have 1 lone pair of electron around iodine. What is the electronic geometry for this molecule? This is A, B, 1, 2, 3, 4. Then E. Total electron pair is 5. So it is trigonal bipyramidal. And its shape is, we have 1 lone pair of electron, AB for E type. So it is molecular geometry seesaw. So D is the correct answer. Okay, question number 4. Question number 4 says, what is the shape of SF5 minus sign? Try to draw the Lewis structure just to predict the shape of this molecule. Both electronic geometry as well as molecular geometry. Sulfur, it has 6 valence electrons and 1 electron is also added. So we have 5 fluorine atoms. Try to draw the Lewis structure. 5 fluorine atom. 1, 2, 3, 4, 5. How many lone pairs of electrons? We have only 1 lone pair of electron for this polyatomic ion. So this is an AB5E type. The total electron pairs are 6. Therefore, The electronic geometry is octahedral. But this question says, what is the shape, molecular shape or molecular geometry of this polyatomic ion? It is shape is square pyramidal because it is an AB5 type. So B is the correct answer for this question. Okay, question number 5. According to Weiss pair theory, what is the molecular geometry of XeF3 plus? Xe, xenon, has 8 valence electron. It forms 3 bonds with 3 fluorine atoms. So we have a charge, 1 positive charge. So it is an AB3E2 type. AB3E2 type. What is the shape, molecular shape for this molecule? It is T shape. So B is the correct answer for question number 5. The last question, question number 6. It says, if a molecule has trigonal pyramidal shape, how many non-bonding pairs of electrons are present in the valence shell of the central atom? We have only one, because trigonal pyramidal shape has a type of AB3E type. We have only one lone pair of electron. So A is the correct answer for this question, and this is all about molecular geometry and the factors affecting the ideal bond angles. Thank you for watching. Thank you for listening. See you next time. Until then, bye bye.